Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 15, Piecewise Functions. Okay, let's recall that the absolute value of a number is the distance from zero of a point on the number line. Because distance is being measured, the absolute value of a non-zero number is always positive. For example, the absolute value of negative 3 equals 3. Because the point, negative 3, located 3 units to the left of 0 on the real number line, is 3 units away from 0. Absolute value can be used to define the distance between any two points on the real number line. For example, the absolute value of 5 minus 8 is 3 because there are 3 units between the number 5 and 8 on the real number line. Okay, so here we go with the classwork. Opening exercise. For each real number a, the absolute value of a is the distance between 0 and a on the number line and is denoted as absolute value of a. Solve each one variable equation. Okay, so we have the absolute value of x equals 6. So when we're solving absolute values, we can be on the right side of the point that they're talking about, or we can be on the left side of that point. So for example, if x was 2, and I told you that it was 6 units to the right, then you would say, well, 2 plus 6 is 8. But if I told you it was 2 units to the left, you'd say, well, 2 minus 6 is 4. So negative 4, I'm sorry. So I know that 8 and negative 4 are both 6 units from 2. Okay, so if I were on this number line, and this is 2, 8 is over here, negative 4 is over here, and the distance between these is both 6. Okay, so that's kind of the way absolute values work. Well, not kind of, it is. So here we go. The absolute value of 6 equals 6. Now keep in mind there can always be 2 possible answers, and that's why I just showed you this. So what you do is you take what's in the absolute value and set it equal to the number, and then you do it again and you say, or x could equal the negative of the other side, because we could be 6 units to the right or 6 units to the left. And then you solve. But in this case, we're done. So the absolute value of 6 is 6, and the absolute value of negative 6 is 6. Okay, so this one, we have a variable and a number inside. So we're saying some number, x minus 5, is 4 units away, or that x minus 5 is on the other side, negative 4 units. And then in solving this, I would add 5 to both sides for this piece. And I get x equals 4 plus 5, which is 9. And then I would add 5 on this one. And then I would say, well, then that gives me x equals 1. Okay, so I just brought in this number line. I really want to make sure you understand what absolute values are. So we had some number minus 5 equals 4, and when I did this we got the answer to be 9, so I'll put a dot there, and we had the answer to be 1. And what we were saying was we are going to be 4 units away from some number, and if I put a dot here, there's 1, 2, 3, 4 to the right, and 1, 2, 3, 4 to the left. So this just basically says the number inside is the opposite sign, and that's the point we're talking about. And we're going to go 4 units to the right and 4 units to, we're going to be 4 units away from it on both sides. That's what absolute value really means. Hopefully that was a clear representation and you understand that. Okay, next one. The first thing I want to do is get the absolute value by itself. It's being multiplied by 2. So let's get rid of that 2 by dividing both sides by 2. And remember, what you do to one side, you do to the other. 2 divided by 2 is 1, and we're left with the absolute value of x plus 3 equals negative 2 divided by negative 10 divided by 2 is negative 5. Then I'm going to take x plus 3 and set it equal to negative 5. I'm going to take x plus 3 and set it equal to 5. Subtracting 3 from both sides here will give me x equals negative 8. Subtracting 3 from both sides here will give me x equals 2. And then you should always plug it back in and check. 2 plus 3 is 5. The absolute value of 5 is 5 times 2 is 10. 10 does not equal negative 10. And then you say, I thought I did this right. Well, let me check the other number. So I take negative 8 and I plug it in. Negative 8 plus 3 is negative 5. The absolute value of negative 5 is 5. 5 times 2 is 10. 10 does not equal negative 10. And then we're like, okay, I made a mistake here. What's going on? But actually, what I'm going to explain to you now is distance can never be negative. So when we're talking about absolute values, an absolute value can never be equal to a negative number. So whenever I have an absolute value on one side and I have a negative number on the other side without any variables over here, I automatically know that there is no solution, and that's the empty set. Or you could say no solution, or you could say the empty set like this, brackets with nothing in it, or just say no solution. Okay? So talking about set notation, now let's go back and do this for these two answers here. So this answer, and I always put them from least to greatest, negative 6, comma, 6. So it's a set of all numbers containing 6 and negative 6. And then this one here is 1, comma, 9. And there you have it. That's how you would solve these. Okay? Now let me just erase this now so it's not in the way for the next problem. Determine at least 5 solutions for each two-variable equation. Make sure some of the solutions include negative values for either x or y. Okay, so all I really need to do here is y cannot be negative in this case. Just keep that in mind. Y has to be positive every single time. X can be positive or negative. Okay, so I'm just going to pick a value for x. And let's just put this in set notation while we're doing it. The absolute value, or this, here's the set, and the first ordered pair is going to be an x comma y, and it said to do 5 solutions. Pick a number, x, negative 4. The absolute value of negative 4 is 4, so y has to be 4. How about negative 2? The absolute value of negative 2 is 2. Y has to be 2. Let's do a positive number, 1. Absolute value of 1 is 1, so y is 1. And then how about 0? Well, the absolute value of 0 is 0, so that'd be the point 0, 0. And then we could do a bigger number like 20. The absolute value of 20 is 20. And there's 5 solutions. Second one. Y equals x minus 5. This is inside parentheses, so we do the opposite. So whatever x is, we add 5 to it, or subtract 5 from it. That's all you have to think about. Either add or subtract 5 from a number. So you just simply pick any number, negative 3, add 5 to it. Negative 3 minus 5 is negative 8. Absolute value of negative 8 is 8. Okay? So when you're dealing with a negative number, I guess you aren't just adding 5. You're subtracting 5 and then taking the absolute value. Okay, so just pick any x. How about 2 this time? 2 minus 5 is negative 3. The absolute value of negative 3 is 3. Again, we could do 0. 0 minus 5 is negative 5. The absolute value of negative 5 is 5. 7. 7 minus 5 is 2. The absolute value of 2 is 2. And finally, I don't know, negative 10. Negative 10 minus 5 is negative 15. The absolute value of negative 15 is positive 15. And there are 5 values. Okay, now x can't be negative. Remember, absolute values cannot equal a negative number, so x has to be a positive number. I cannot plug in any values where x is negative. So I will start with 0, and the absolute value, now we're, time out. Let's substitute in for our y, not our x. So let's make x 0, or y 0, I'm sorry. The absolute value of 0 is 0. Okay, now we're going to plug in y and calculate x. We're working backwards this time. So now let's do a negative 3 for y. Absolute value of negative 3 is 3, so x is 3. And let's pick another y, this time make it positive 2. Absolute value of 2 is 2. And, I don't know, 17. 17. So let's make y 17. The absolute value of 17 is 17. And then how about negative 40? I can't put that in for x. I keep forgetting that we're working backwards here. Negative 40 for my y. Absolute value of negative 40 is positive 40. And there's 5 solutions. Exploratory challenge. For parts A through C, create graphs of the solution set of each 2 variable equations from opening exercise 2. So A is y equals the absolute value of x. So here you could do a table and do x comma y. I like working around the center, and the center is when the inside the absolute value equals 0. So when x is all by itself, 0 is where this is going to have its vertex. It's either maximum or its minimum value. So when the absolute value of 0 is 0, so that would plot the point 0, 0. So I'm going to go 1 to the left on x, negative 1. Absolute value of negative 1 is 1. So x is negative 1, y is 1. And then I'll do x is negative 5. So negative 5, the absolute value of, oh, I forgot to put this, 1. The absolute value of negative 5 is positive 5. So I'm going to graph the point negative 5, 5. Left 5, up 5. And then how about negative 10? Absolute value of negative 10 is 10. That means left 10, up 10, right there. And then I draw a nice, neat, straight line. Obviously, I can do this with my program. You can do this with a ruler. Okay, so there's my left side. Now I've got to complete the right. So to the right, how about I use the point 2? The absolute value of 2 is 2, so I go over 2, up 2. That's right here. How about 4? The absolute value of 4 is 4, so that's over 4, up 4, which is here. And then how about 10? Absolute value of 10 is 10, so that's over to the right 10 and up 10 right there. And then I draw a straight, neat line with a ruler if you're not using a program like me. And you draw a nice straight line like so. And there is the absolute value of x. Now let me elaborate a little on the center. So I always like to make sure I have the vertex, because say I pick points over here starting at 1 and only went to greater than 0. Well, then I would only see a linear equation. I wouldn't see where the vertex was and how it turned on the other side. So I like to know where this point is, and that point is when what is in the absolute value equals 0. So what minus 5 is 0? And I know that the answer is 5. So I put 5 in the middle of my t-chart. So when x is 5, 5 minus 5 is 0. The absolute value of 0 is 0. So I'm plotting the point 5, 0, which is right here. And then I'm going to go to, I don't know, how about 10? Or how about 7? Let's do 7 first. 7, the absolute value of 7 minus 5, which is 2. The absolute value of 2 is 2. So I'm going to go over 7 up 2. And then if I substitute in 10 for x, 10 minus 5 is 5. The absolute value of 5 is 5. So I go over 10 up 5, and there's my point. Working the other way, I could go to 2. 2 minus 5 is negative 3. The absolute value of negative 3 is 3. So I go over 2 up 3. Okay, and then I could do a number like, I don't know, negative 2. Negative 2 minus 5 is negative 7. The absolute value of negative 7 is 7. So I go left 2 up 7, and that's right here. And then I draw my lines. Okay, so please use a ruler doing this. Accuracy starts to get really important when you get into the higher math classes. Okay, there's one, and there's the other. So there's my absolute value of x minus 5. And actually, whenever I graph anything, I really should label my graph. So I should write here y equals the absolute value of x minus 5. And over here, I should write y equals the absolute value of x. Like so. Label the graph. And another thing, these do go on forever, so I should have arrows at the ends here as well. Okay, page 2 brings us to part C, another example. So the first thing I'm going to do is make a table x comma y. Now this one's backwards. So it's x equals an absolute value of y. So again, nothing changes. Our vertex is going to occur when y, or what's in the absolute value bracket, is 0. So what makes y 0? Well, that would be 0. But notice I'm putting it over on this side. And then I take the absolute value of the y and put the absolute value over here. So I am plotting the point 0, 0. But if I choose y, now keep in mind x cannot be negative. But it doesn't matter what x is, as long as I substitute in values for y, I should never get a negative number anyway. So if I go to negative 2 for y, the absolute value of negative 2 is 2. So that is the point 2 comma negative 2, which means go right 2 down 2. So that's right here. So I'm going to continue in that direction. Let me get these out of the way. I just wanted to clarify with you that those are points when they're in the table. Okay, so now let's go negative more on the y. And how about negative 5? The absolute value of negative 5 is 5. So I'm going to plot the point 5 comma negative 5, which is right 5 down 5. Okay, and then I'm going to do one more. And how about negative 10? The absolute value of negative 10 is 10, which tells me to go right 10 down 10, and that's right here. So I'm just going to stop right there, and I'm going to plot that. I'm going to graph that line just on those points. I'm not going to assume it's going anywhere else. Okay, let's try that again. Thin, blue. What is going on? This, 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 blue. There, that's better. So approximately right there. Okay. Now I'm going to go to the other side of 0, that is, the positives. And this time I'm just going to choose different values in these just to show you that it will still be a straight line. 1. The absolute value of 1 would make x 1. So that's the point over 1 up 1. So look what's happening this time. Now if I pick 5 for the y, absolute value of 5 is 5, which is over 5 up 5, which is here. And then finally, if I choose 10, the absolute value of 10 is 10, so that's the point right 10 up 10, which is here. Then when I go to plot that number, or that line, going through all those points, this is what I'm going to get. Okay? So this is the absolute value of y equals x. So if I were to label this diagram, I'd say x equals the absolute value of y. So it looks like y equals the absolute value of x. It's just rotated 90 degrees, if you will. And keep in mind, if you don't recall, there's what's called a vertical line test. And the vertical line test says that if you draw a vertical line and you cross it more than once, your function hits it more than one time, then it is not a function. So I shouldn't say your function. The graph crosses the vertical line, it fails the vertical line test. This is not a function. It's a relationship or a relation, but it's not a function. Okay, now it says to write a brief summary comparing and contrasting the three solution sets and their graphs. So we can say the graphs of part A and B are the same. So if I go back and look while I say this, the graphs of part A and B are the same, except part B has a point of the V, the vertex of angle, at 5, 0 instead of 0, 0. Okay, so what they're saying is the vertex is at 5, 0, the vertex here is 0, 0, so this is a graph of this just shifted 5 units to the right. The graph of part C looks like a 90-degree clockwise rotation of the graph from part A about the point, the origin. The points in the solution set to parts A and B are a function, but the points in the solution set for part C are not a function, as I stated already. Okay, for part E through J, consider the function f of x equals the absolute value of x, where x can be any real number. Explain the meaning of the function f in your own words. So try this, pause the video, and then come back and check. Okay, so here's a possible explanation. This function assigns every real number to its absolute value, which is the distance the point is located from 0 on the real number line. Each number and its opposite will have the same range element. Number 0 will be assigned to 0. So f says to state the domain and range of this function. So keep in mind, this is the absolute value of f of x. Where's its vertex? Well, its vertex is 0, 0. And domain is your x values, and range is your y values. So the domain, your x values, x can be negative because a negative 3's absolute value is positive 3. So the domain, I'll use the letter D, the domain is the set of all reals. So I can just represent that as a capital R with a line through it. That means the set of all reals, or you could just write the words all reals. Any number you can plug in for x, you can get an absolute value of it. The range, however, is going to have a minimum value when x is 0. So if I take the absolute value of 1, I get 1. If I take the absolute value of negative 1, I get 1. I cannot get a negative value, so the range is the set of all numbers where x is greater than 0. So you can either say this, you could say all positive numbers, or the range could be from 0, actually it can include 0, so that's a bracket. So if I did this in set notation, it would be 0, comma, infinity, with an open bracket. And so the set of all reals would be negative infinity to infinity, if we used set notation. Okay? G says create a graph of the function f. You might start by listing several ordered pairs that represent the corresponding domain and range elements. Okay, so we've already done this. It was example 1, I believe. So all you're doing is substituting in values. So 0, the absolute value of 0 is 0. 5, the absolute value is 5. 10, absolute value of 10 is 10. Negative 5, the absolute value of negative 5 is positive 5. And then finally, negative 10, the absolute value of negative 10 is 10. And then use a ruler on your paper. Accuracy, accuracy, accuracy. Oops. This. this. Bear with me, I'm struggling. All right. And like so. So there it is. There's the graph corresponding to that domain and range. So the reals can be any negative. I can go forever and ever and ever this way. So when it means you can go forever, it means you should have arrows here. Just like that. So it's going left forever, it's going up forever. But it stops going down to zero after 0. Once it gets to 0, it does not go lower. Okay, page 3 brings us to part H. How does the graph of the absolute value function, and when they say that, they're talking about the function f of x equals absolute value of, I'm sorry, f of y. Okay. Well, let's see, what are they using before I just assume one way or the other. F of x equals, okay, f of x means that what is y? F of x, this term f of x just simply means what is y when we take the absolute value of x. So f of x equals the absolute value of x is what they're talking about here. F of x equals the absolute value of x. So how does the graph of the absolute value function compare to the graph of y equals the absolute value of x? Well, f of x is y. So these things, these two equations are identical. So we would say the two graphs are identical. They are identical because each ordered pair in the function would make the equation y equals absolute value of x a true number sentence if the domain value were substituted for x and the range value were substituted for y. Therefore, the graph of the function is the graph of the solution set of the equation. Okay, so now it says define a function, okay, whose graph would be identical to the graph of y equals the absolute value of x minus 5. So all they're asking you to do here is change y to function notation. So I know I'm going to get the absolute value of x minus 5 on the right. That's not going to change. But I'm going to change my y to naming it something. We could be a of x, b of x, c of x, d of x, anything like that. How about just using g of x, for example? So there's a function whose graph would be identical to y equals absolute value of x minus 5. G of x equals the absolute value of x minus 5. These are absolute value brackets. J, could you define a function whose graph would be identical to the graph of x equals the absolute value of y? Explain your reasoning. Now you need to be careful here because we're working, y is our range and x is our domain. And remember, when we graphed that, we ended up with this. And it failed the vertical line test, which means it is not a function. So could you define a function whose graph would be identical to this? And the reason's no. The graph of x equals the absolute value of y does not meet the definition of a graph of a function. If it were the graph of a function, say the function h, it would be the set of ordered pairs x comma h of x, where x is in the domain, which means there would be only one y value for each x in the domain D. However, in the graph of x equals the absolute value of y, there is a number x. In fact, there are infinitely many x's associated with two different y values. 3, 3, 3, negative 3 are both solutions to the equation x equals the absolute value of y. All right, much more detailed explanation there. Part K. Let f sub 1 of x equal negative x for x that are less than 0, or you can just say for x's that are negative. And let f sub 2 of x equal x for positive or equal to 0. X's that are positive or equal to 0. So greater than or equal to 0 means positive numbers, but and including 0. So graph the function f1 and f2 on the same Cartesian plane. How does the graph of these two functions compare to the graph in part G? So where's the graph in part G first? So the graph of G is right here. That's just the absolute value of x. So now we're saying let f sub 1 of x equal negative x for x is less than 0, and let f of 2 of x equal f sub 2 of x equal x for the x's that are positive or 0. Okay, this might be a little confusing to you, but let me try to explain this. So if I say f sub 1 of x equals negative x when x is less than 0, and I do a table, x comma y. All right, f of x is my y, equals negative x for any values that are less than 0. So I'm only picking x's that are less than 0. So how about negative 1, negative 5, negative 10? So what this is saying is when you pick those values, you plug it in here. So it would be f of x equals the negative of this negative number. Well, that would mean a negative, negative 1, which equals positive 1. So this would be 1. A negative, negative 5 would be 5. And a negative, negative 10 is 10. So that'd be negative 1, 1, negative 5, 5, negative 10, 10, and then connect the dots, the points. Okay, and it's going to go down to 0 but not include 0. So when I graph that, I don't want to include 0, and in doing so, I put an open circle at 0. So that is the left side for values less than x. So I could go all the way up to negative 0.000001, which is just a smidgen to the left of 0, but 0 is not included, so I put an open circle there. Okay, now let me do the other side in green. Now we're saying f sub 2 of x equals x for values where x is greater than or equal to 0. So then I take and I make a t-chart, x, y. Now f sub 2 of x is my y, x is my x greater than or equal to 0, so I'll start with 0. I will put 1, 5, and 10. The absolute value of 0, so f sub 2 of x equals x. So y equals x, y equals x, y equals x, y equals x. That's all that's saying. 0, 0. Now I shade this in because it's on the green side. 1 equals 1, or 1 comma 1, 5 comma 5, and 10 comma 10. And then I draw a line segment with a ruler. Okay, and there we have it. There is the graph of this piecewise function. f1 is blue, f2, or f sub 2 is green. Definition. The absolute value function f is defined by setting the f of x, the function, equal to the absolute value of x for all real numbers. Another way to write f is as a piecewise linear function. So you can say f of x equals negative x. This is the blue. That is a line with a negative 1 slope, y-intercept of 0, but not including 0. And then f of x equals x for x is greater or equal to 0. That's just a line with a slope of 1, y-intercept of 0, positive. And that's the green line. So an absolute value function is really a piecewise function of two linear equations that come together at the vertex. Okay, page 4 brings us to example 1. Let g of x equal the absolute value of x minus 5. The graph of g is the same as the graph of the equation y equals the absolute value of x minus 5. So they're basically telling you right there that g of x is the same as y. You drew in exploratory challenge 1 part B. Use the redrawn graph below to rewrite the function g as a piecewise function. So I've marked this red and I marked this side green because those are our two pieces to our piecewise function. So you label the graph of the linear function with negative slope by g sub 1, okay? And the graph of the linear function with the positive slope by g sub 2. So they labeled it for us here, graph of g sub 1 for x less than 5. So any x is less than 5, we're going to use this function here. Graph of g sub 2 is the positive slope function for any value of x that equals 5 or is greater. So since it equals 5, I would have a green dot here. The red is not included at 5. It comes close to it, but never approaches or never gets to the point 5. It'd get to 4.999 repeating, but never get to 5. Okay, so function g sub 1, the slope of g sub 1 is negative 1. Why? And the y-intercept is 5. So if you look here, if you take this point here, you go down 1, right 1, down 1, right 1, down 1, right 1. That is a slope of negative 1. That is rise over run. We rose a negative 1 and we went right 1. And the y-intercept is 5, which is right here, y-intercept of 5. So therefore, g sub 1 of x equals negative x plus 5. Okay? So it's a slope with negative 1 and a y-intercept of 5. So negative x plus 5. So notice these two are different. And then when we go to function g, the slope of g sub 2 is 1. Why is that? Well, if we start here, we go up 1 over 1. Rise over run is 1 over 1, which is 1. Up 1 over 1, up 1 over 1, up 1 over 1. This is a positive 1 slope. So slope is in front of the variable, so that's positive 1 instead of negative. So it's 1. And then we have to continue that function. So I'm going to do this with a dashed line. So just to make this really clear, go back to here, and then if I did hello, try that again, a line, dashed, thin, green, and then if I went like this and I continued it, it doesn't go this way, that's why I'm using a dashed line. But if it did, then its y-intercept would be negative 5, which is our b. So slope of 1, y-intercept of negative 5. So if we continued, if we wanted to get the y-intercept, we'd have to plug in negative 5 for x. Or I'm sorry, 0. Plug in 0 for x. 0 minus 5 is negative 5. Okay, so this dashed line is not part of our function. This is one piece, that's the other piece, but I'm just showing you that if this piece continued downward beyond our vertex, it would have a y-intercept of negative 5. That's right here. All right, exploratory challenge 2. The floor of a real number, x, denoted by the absolute value of x, is the largest integer not greater than x. The ceiling of a real number x, denoted by the absolute value of x, oh, I'm sorry, is that absolute value? Or is that, yes, I guess it is the smallest integer not less than x. The sawtooth number of a positive number is the fractional part of the number. Oh, those aren't absolute values. These are brackets, by the way. These look like this. Okay? That is not absolute value. So I was wondering when they're calling floor and ceiling. Okay, the sawtooth number of a positive number is the fractional part of the number that is to the right of its floor on the number line. So in general, for a real number x, the sawtooth number of x is the value of the expression x minus the bracketed x, which is the greatest integer, actually. Each of these expressions can be thought of as functions with a domain being the set of real numbers. Okay, page 5 brings us to a better explanation of what I just read to you. You're probably going, what? Floor, ceiling, what's all this about? It's called the greatest integer function. And all it means is you just round, and there's no decimals in your graph. So let's take a look. So see this 4.8, that's our x. The floor equals the absolute, or the floor equals the greatest integer. What is the greatest integer that's less than 4.8? In other words, round down. So just ignore the decimal, and it's 4. But be careful with negatives. So here's a number line. Here's 0. Here is -1. Here is -2. -1.3 would be about here. Go to the next integer to the left. That's rounding down. -2. So if you have a positive number, here's 0, here's 2, here's 1. 2.2 would be over here. Round down, go to the left on your number line, and the first integer is 2. If you have that number, it's just that number. If you have that number, it's just that number. -2/3 is right about here. It's not even -1. So when I round down, it would be -1. Or find the first integer to the left. Pi is 3.14. Move to the left. What's the first integer to the left of 3.14? 3. Okay, so then we're going to go to the ceiling. And all that means is round up. 4.85. So we're moving 1 unit to the right now. So if I have this number line here, the first two were done for us. 2.2, well, here's 2. Here's 3. 2.2 would be over here. What's the first number to the right of it? That's an integer. 3. 6 is just 6. -3, simply -3. So if it is an integer, it's that value. So the floor and ceiling are the same. -2/3, which was right here. Now I move to the right, and my first integer to the right of that fraction is 0. Pi is 3.14, which is here. So now I'm going to the right to 4. Okay, hopefully that makes sense to you. Just simply rounding down and rounding up. Alrighty then. So then we have the sawtooth. X equals x minus the greatest integer. So the first one's done for us. So we took 4.8 minus the floor. 4.8 minus the floor is 0.8. 4.8 minus 4 is 0.8. 1.3 minus 2 minus a -2 is +2. Okay, be careful with the negatives. -1.3 minus a -2, because we're subtracting this number, is the same as saying +2. All right, so let me get my calculator out to verify. -1.3 right here minus a -2. Enter. 0.7. So it's saying +2, or 2 minus 1.3. 2.2 minus 2 is 0.2. Let me change. I thought I changed colors here. I did. Green's highlighted, but it's not working. How about this? 2.2 minus 2 is 0.2. There's green. All right. Okay, 6 minus 6, 0.0. -3 minus a -3 is +3. -3 plus 3 is 0.0. -2/3 minus a -1 is -2/3 plus 1, or 1 minus 2/3, and that is 1/3. And then pi is 3.14159, blah, blah, blah. -3 is 0.1459. I'm not going any further. 3.14159. Forgot my 1. Okay? Or you could have just gone to your calculator and hit second, caret is the pi, and hit enter. 3.141592654. So I have 3. So 3.1, that minus 3 is just the decimal position, 0.14159, blah, blah, blah. Okay, since this goes on forever and ever, we could also just say, well, how about just pi minus 3? All right, now it says create a graph for each function. Floor. Let's use the same color we used here, which is black. Floor. So 4.8. So this is x, this is y. So if I go over 4.8, 1, 2, 3, 4.8, I'm off the graph here. These aren't very good graphs. But anyway, if we, let's see, create a graph of each function floor, x to equals the greatest integer. All right, so what that means is if it is equal, it's included. So since we had 6, the value is 6. So if I went up 6, I'd put a dot. So I'd go over 6, up 6, put a dot. 0, 0, put a dot. 1, 1, put a dot. Okay? 2, 2, put a dot. 3, 3, put a dot. Now, here's how I'm going to explain this. Now, if I wanted to graph 2.2, that means go over 2.2 and go up, and the line is going to be here. You're going to round down, but you're not going to include this endpoint because it pops up here. So then if you do that for all of them, you're going to get this. And this won't be included because it's here, and then go over and it's included here. So if I picked negative 2/3, that means left 2/3, I went down 1. Left 2/3, down 1, I'm on that line right there. Hopefully that makes sense. If I go over 3.14 pi, 1, 2, 3.14 is here, I should go up 1, 2, 3, so I should have a line here. But I'm not going to include the right end because it's going to hop up to 4 or 5 or whatever line you're on. Okay, so now graphing the ceiling, if I go over to 6, it's 6, 6. So if I go over 1, 2, 3, 4, 5, 6, I go up 6, I put a dot. Okay? Okay, these aren't the best graphs to represent this, so I'm trying to find points that are actually here. Let's go to this one. Negative 2/3 would be left 2/3, and then it says up 0. So I know my line is going to be here. Okay, but if I have an integer like 6, it's just going to be 6, 6. So it's going to be 1, 1. That's going to be a point. And 0, 0 is going to be a point, but the other end is going to be open. Okay, so then it just repeats. So I'm going to bring a line over here and put a circle there. So negative 3, that means go over 3 and then down 3. We're graphing the ceiling. Negative 3 is 1, 2, 3 to the left, 1, 2, 3 down, and I put a dot. And then anything after that's going to go to the left. So that repeats, and once you figure out what it's doing, then you just repeat it on every one. They call it a sawtooth or a stair graph. I've heard it called staircase. So this is going to be a solid point over to an open point. Open point here, over to solid. So it's the point that we're including and the point we're not including are just flipped around on these two graphs. I made a mistake too. This one here. should be open here and go over to here, including this with a line in between. All right, now the sawtooth is x minus, so it's this graph. So it's going to be x comma this, 4.8. So I go over 1, 2, 3, 4, almost 5, and I go up 0.8, which would be about here. Let me change it to green. It'd be about here. If I went over 1.3, I'd go up 0.7. Let's just graph these first. 2.2 to the right, up 0.2. So 2.2 to the right, up 0.2. If I went 2.3 to the right, I'd go up 0.3. 2.9 up 0.9. So what this is doing, it's going up at an angle. It's going to include this point. So if I had the point 0.66, which isn't on this graph, that's why this is bothersome. If I had 1, it'd be over 1, up 1. Okay. So I'd have 0 and all the way up to 1. 1 minus 1 is 0, all the way up to here. -1 minus a -1 is +1, which is 0. So all these points start at 0, and we're just going up to 1, but not including it, like so. That one's a little harder to understand. So these all would go up, and those would be open like so at an angle. That is the sawtooth. Part C says, for the floor, ceiling, and sawtooth functions, what would be the range value for all real numbers x on the interval 0, including 1, the interval 1, not including 1, to 2, including 2, the interval including -2 over to -1 but not including it, and the interval 1.5 to 2.5 inclusive. Okay. So it says for all three of these, we're going to do each one of these. Okay. So I'm just going to make a table here, and I'm going to say floor, ceiling, and sawtooth. Okay, and then I'm going to put the intervals over here. And if I choose the interval from 0, including 0, to 1, on this chart, so that's from here to here, not including 1, then it's asking me what would be the range. And the only value that it's covering in the y's is 0. Okay, the range is simply 0. In this one, the range from 0, including 0, to 1. So if we're including this point here, we're talking about the value y of 0, but then it jumps up, and these y values are 1. So for ceiling, we have a range from 0 and the number 1, but nothing in between, because it jumps. For the sawtooth, from 0 to 1, not included, the range goes from 0 to 1 inclusive, so I would just say including 0, comma, but not including 1. Okay? It's a little confusing, but take your time. Now we're going to do from the interval 1 to 2, inclusive. So we're starting at 1, but not including it on the floor, to 2. So not including 1 to 2, inclusive. Well, if we're in anywhere here, we're at 1. But once we get to the number 2 and we're including it, it jumped up to 2. So this is going to be the points 1 and 2 for our y values. If I start at 1 here, which is right here, and I go to 2, so I want my domain to go from here to here, not including 1, but including 2, then this would just be the value 2. Okay? Let me get rid of that. Sawtooth. Going from 1, not including it, which would be here, up to 2 inclusive. But it's going to go, so it's going to be all values between 0 and 1. But we're not including 1 here. So we're not including 0. We're going to start just above 0. So this would be open, 0, comma, 1, open. We're not including the bottom or the top because we're not including 1 here. And 1 is the point 1, comma, 0. But we're not including 1, so we can't include 0. So that's why this is open and not a closed bracket like up here. Okay, so that's that one. Now we're going to do -2, including -2, to -1, but not including it. So that means go to -2, which is down here. So I need to finish my graph and go low enough. So this would have an open circle here, closed circle here, shaded in between. Okay, so now let me switch back to purple. So we're saying include -2, which is here, but do not include -1. So I'm going to go all the way over here and stop. So my range is simply -2. All right, now if I come over to this one, I want -2 to -1. So go 1, 2, so we're down here. We're going to include -2, but there's nothing there, but there is, it's right here. So that is the point -2. And then we move till we get to -1. So we're going to jump up and we're going to go until we get to -1, but not include it. Those are all the values where x is, or y is -1. So my range is the points that include -2 with our y and -1 on our y. Now the sawtooth, starting at -2, here's 0, -1, -2, starting at -2 and including it, going all the way to -1 but not including it. So we're going up but not including -1. So the range is 0 inclusive, including 0. This is a 0. And it goes all the way up to 1, but it does not include 1. All right, last time. Let me pick a color that I haven't used in my graph. How about orange? Now we're going to do 1.5 to 2.5, including the endpoints. So 1.5 is here, so I'll put a dot here. 2.5 is right here. So we are picking all values in between here. So that includes these pieces and this piece here, and those y values are 1 and 2. All right, over here, go over 1.5. 1.5 is right here. 2.5 is right here. What y values are in between those? 2 and 3. And then finally over here, go over 1.5. So I'm picking all values here to 2.5 here. So this would start at 0.5, go up to 1, and then drop back down to 0.5, but it would be 0 to 0.5. So it would be 0 to 0.5, and then 0.5 to 1, but not including 1. So that would be a total, putting those pieces all together, from 0 to 1, but not including 1. Okay, page 6 brings us to the relevant vocabulary for this lesson. Please review these vocabulary terms, these vocabularies. I don't know if that's a word. Anyway, please review the vocabulary for this section and go do your problem set.